Chapter 29, Reflection and Refraction. This slide is important because it demonstrates the law of reflection, and that is that the angle of incidence equals the angle of reflection. So for a mirror surface, or a very, very shiny surface, the angle of incidence equals the angle of reflection. The direction of incidence and reflected waves is best described by straight line waves, straight line rays. Incident rays and reflected rays make equal angles with a perpendicular to the surface called the normal, as shown in figure 29.3. The angle between the incident ray and the normal, called the angle of incidence, is equal to the angle between the reflected ray and the normal, called the angle of reflection. The law of reflection describes the relationship between the angle of incidence and the angle of reflection. The law of reflection states that the angle of incidence and the angle of reflection are equal to each other. The incident ray, the normal, and the reflected ray all lie in the same plane. The law of reflection applies to both partially reflected and totally reflected waves. 29.3 Mirrors. Consider a candle flame placed in front of a plain, flat mirror. Rays of light leaving the candle are reflected from the mirror surface in all directions. The number of rays is infinite, and every one obeys the law of reflection. Figure 29.4 shows only two rays that originate at the tip of the candle flame and reflect from the mirror to your eye. Note that the rays diverge, spread apart from the tip of the flame, and continue diverging from the mirror upon reflection. These divergent rays appear to originate from the point located behind the mirror. Let me say that again. Note that the rays diverge, spread apart from the tip of the flame, and continue diverging from the mirror upon reflection. These divergent rays appear to originate from a point located behind the mirror. Your experience is that light travels in straight lines. Therefore, you perceive the candle flame to be located behind the mirror. A virtual image is an image that appears to be in a location where light does not really reach. Plane mirrors produce only virtual images. Figure 29.5. For reflection in a plane mirror, object size equals image size, and object distance equals image distance. The law of reflection still holds for curved mirrors as illustrated in figure 29.7. However, when a mirror is curved, the sizes and distances of object and image are no longer equal. The virtual image formed by a convex mirror, a mirror that curves outward, is smaller and closer to the mirror than the object is. When the object is closer to a concave mirror, a mirror that curves inward like a cave, the virtual image can be larger and more distant than the object. As a matter of fact, the image has to be, for this to be true, the image has to be between the mirror surface and the focal point for you to receive an upright image. 29.4. Diffuse reflection. When light is incident on a rough surface, it is reflected in many directions. Diffuse reflection, as shown in figure 29.8, is the reflection of light from a rough surface. Although each ray obeys the law of reflection, the many different angles that incident rays encounter at the surface cause reflection in many directions. 29.8. Diffuse reflection occurs when light is incident on a rough surface. Light that reflects from this page is diffuse. The page may be smooth to a long radio wave, but to a short wavelength of visible light, it is rough. Rays of light incident on this page encounter millions of tiny, flat surfaces facing in all directions, so that they are reflected in all directions, as illustrated in figure 29.9. You could refer to the book for 29.9 and 29.10. A microscopic view of an ordinary paper surface is shown in figure 29.10. Diffuse reflection allows us to read the page from any direction or position. We see most of the things around us by diffuse reflection. 29.5. Reflection of sound. An echo is reflected sound. The fraction of sound energy reflected from a surface is more when the surface is rigid and smooth, and less when the surface is soft and irregular. Sound energy that is not reflected is absorbed or transmitted. Sound reflects from all surfaces: the walls, ceiling, floor, furniture, and people of a room. People who design the interiors of buildings, whether office buildings, factories, or auditoriums, need to understand the reflective properties of surfaces. The study of sound is called acoustics. When a wave that is traveling at an angle changes its speed upon crossing a boundary between two media, it bends. Water waves bend or refract when one part of the wave is made to travel slower or faster than another part. Refraction is the bending of a wave as it crosses the boundary between two media at an angle. Water waves travel faster in deep water than in shallow water. Figure 29.14a shows a view from above a straight wave crest, the bright lines moving towards the right edge of the photo. They are moving from deep water across a diagonal boundary into shallow water. At the boundary, the wave speed and direction of travel are abruptly altered. Since the wave moves more slowly in shallow water, the crests are closer together. If you look carefully, you'll see some reflection from the boundary. In drawing a diagram of a wave, it is convenient to draw lines called wave fronts that represent the position of different crests. At each point along a wave front, the wave is moving perpendicular to the wave front. The direction of motion of the wave can thus be represented by rays that are perpendicular to the wave fronts. The ray in figure 29.14b shows how the water wave changes direction after it crosses the boundary between deep and shallow water. Sometimes we analyze waves in terms of wave fronts, and at other times in terms of rays. Both are useful models for understanding wave behavior. Here are some figures that I will be referring to in the next few slides. The first one, figure 29.15, the wavefronts of sound are bent in air of uneven temperature. The next one, 29.16, at night, when the air is cooler over the surface of the lake, sound is refracted towards the ground and carries unusually well. In 29.17, as a light wave passes from air into water, its speed decreases. So it will go towards the normal. And as a light wave goes from water into air, it goes away from the normal. As illustrated here in figure 29.18, the laser beam bends towards the normal when it enters the water and away from the normal when it leaves the water. As figure 29.19a shows, a thick pane of glass appears to be only 2/3 its real thickness when viewed straight on. For clarity, the diameter of the eye pupil is made larger than true scale. Similarly, water in a pond or pool appears to be only 3/4 its true depth. In figure 29.19b, the fish in the water appears to be nearer to the surface than it really is. It also seems closer. Another illusion is shown in figure 29.19c. The light from the root beer is refracted through the sides of the thick glass, making the glass appear thinner than it is. The eye, accustomed to perceiving light traveling along straight lines, perceives the root beer to be at the outer edge of the glass along the broken lines. These effects are due to the refraction of light whenever it crosses a boundary between air and another transparent medium. 29.9, Atmospheric Refraction. Although the speed of light in air is only 0.03% less than its speed in a vacuum, in some situations atmospheric refraction is quite noticeable. One interesting example is the appearance of a distorted image called a mirage. A mirage is caused by the refraction of light in Earth's atmosphere. On hot days, there may be a layer of very hot air in contact with the ground. Since molecules in hot air are farther apart, light travels faster through it than through the cooler air above. The speeding up of the part of the wave nearest the ground produces a gradual bending of the light rays. This can produce an image, say, of the palm tree in figure 29.20. The image appears upside down to an observer at the right, just as if it were reflected from a surface of water, but the light is not reflected, it is refracted. Wavefronts of light are shown in figure 29.21. The refraction of light in air, in this case, is very much like the refraction of sound in figure 29.15. Undeflected wavefronts would travel at one speed and in the direction shown by the broken lines. Their greater speed near the ground, however, causes the light ray to bend upward as shown. A motorist experiences a similar situation when driving along a hot road that appears to be wet ahead. the sky appears to be reflected from the wet surface, but in fact, light from the sky is being refracted through a layer of hot air. A mirage is not, as some people mistakenly believe, a trick of the mind. As figure 29.22 illustrates, a mirage is formed by real light and can be photographed. 29.10 Dispersion in a prism. Chapter 27 discussed how the average speed of light is less than c in a transparent medium. How much less depends on the medium and the frequency of the light. Light of frequencies closer to the natural frequency of the electron oscillators in a medium travel more slowly in the medium. This is because there are more interactions with the medium in the process of absorption and re-emission. Since the natural or resident frequency of most transparent material is in the ultraviolet part of the spectrum, visible light of higher frequencies travels more slowly than light of lower frequencies. Violet light travels about 1% slower in ordinary glass than red light. Light waves of colors between red and violet travel at their own intermediate speeds. Since different frequencies of light travel at different speeds in transparent materials, they will refract differently and bend at different angles. When light is bent twice at non-parallel boundaries, as in a prism, the separation of the different colors of light is quite apparent. This separation of light into colors, arranged according to their frequencies, is illustrated in 29.25, is called dispersion. Here is the anatomy of a rainbow. So this is the primary rainbow or the inner rainbow, and you can see that it's curved in the upper right hand part of the slide. The inner color is going to be violet. The outer color is going to be red. 42 degrees for red, 40 degrees for violet. Look at those light rays. That's going to be very important. Look at the 42 degrees and the 51 degrees. That's also going to be very, very important. Here's the anatomy of the second rainbow. And you see that the outer band now is violet and the inner band is red. So that's going to become very, very significant when you look at the pictures of the double rainbow. The primary rainbow is the inner, and the outer rainbow is the secondary rainbow. And here's a computer enhanced picture of a double rainbow event, and you could see that the outer, you could see the inner rainbow, and you could see that it's clearly red at the outer band, and it's violet on the inner band. And then on the secondary rainbow, the inner band is red and the outer band is violet. Here's another picture which shows that same idea. The outer band of the inner rainbow, or the primary rainbow, is red, and the inner band of the secondary or outer rainbow is red. Look at the area inside the primary rainbow. It is very light, and the darkest area is actually between the two rainbows. That's also very significant. The critical angle. At a certain angle called the critical angle, you'll notice that a beam no longer emerges into air above the surface. The critical angle is the angle of incidence that results in the light being refracted at an angle of 90 degrees with respect to the normal. As a result, the intensity of the emerging beam reduces to zero. When a flashlight is tipped beyond the critical angle, 48 degrees from the normal in water, the beam cannot enter the air. It is only reflected. The beam is experiencing total internal reflection, which is the complete reflection of light back into its original medium. Total internal reflection occurs when the angle of incidence is larger than the critical angle. The only light emerging from the water surface is that which is diffusely reflected from the bottom of the bathtub. Optical fibers. Optical fibers, sometimes called light pipes, are transparent fibers that pipe light from one place to another. As illustrated in figure 29.35, they do this by a series of total internal reflections. Optical fibers are useful for getting into inaccessible places. Mechanics and machinists use them to look at the interiors of engines, and physicians use them to look inside a patient's body. Light that shines down some of the fibers illuminates the scene and is reflected back along others.